discussed in the last class that we have looked into the definitions and various properties of matrices and determinants, and looked into so many. We recapitulated some of the old ideas and the definitions of whatever we have done in earlier years in our earlier classes. The properties and various properties of the matrices and determinants which will be satisfied, classification of different matrices, which one is called a symmetric matrix, asymmetric matrix, diagonal matrix, skew symmetric matrix, and various properties of them we have already seen. Now, at the end we have defined the eigenvalue problem, and eigenvalues are quite important in all chemical engineering applications. So, let us start from that point onward. If we write A x is equal to lambda x, we have already seen what is the concept of matrix, and matrix is nothing but an operator. It operates on a vector x and it returns a value it maps into x. So, a matrix is not like a function, it is an operator, and if we are able to write the form of the matrix in this particular fashion, A x is equal to lambda x, where lambda is a multiplier, is a scalar. We call this problem as a standard eigenvalue problem. Okay. So, if you bring A x the lambda x on the other side, it becomes A x minus lambda x is equal to 0. So, we can represent A minus lambda I should be equal to multiplied by x, this should be equal to 0. So, therefore, this equation is sort of a homogeneous algebraic equation. So, this is absolutely homogeneous equation. There is no non-homogeneous term present on the other side. If we have if the form of this equation is A minus lambda I times x is equal to b, this is a non-homogeneous equation. Now, for equation 1, x is equal to 0 is a solution. Of course, if x is equal to 0, then that is a solution, and this is known as a trivial solution. Therefore, the necessary and sufficient condition for so we are not looking for the trivial solution, we are looking for the non-trivial solution. The necessary and sufficient conditions for non-trivial solution is that determinant of A minus lambda I is equal to 0. Condition for non-trivial solution is determinant of A minus lambda I is equal to 0, and determinant of this is if A is a square matrix of size n cross n, then this equation will gives you the determinant of A minus lambda I is equal to 0. This equation gives a polynomial of lambda. Finally, it gives a polynomial of lambda that is p of lambda is equal to 0, degree of the polynomial. So, this is known as the characteristic equation. This p of lambda is equal to 0 is known as a characteristic equation. If the for a matrix square matrix n into n, then the order of this degree of this polynomial is n. So, for n into n matrix, we are talking about nth degree p lambda is equal to 0 becomes an nth degree of nth degree polynomial. The roots of this polynomial of p lambda may be real, it may be complex conjugate. Okay. So, therefore, these roots can occur either a complex conjugate pair and or real valued system, and these roots are called eigenvalues. Eigenvalues of the system, and the corresponding solution, the solution corresponding to eigenvalue is called eigenvector. Suppose there are lambda I is a set of real valued or complex valued eigenvalues. I is the lambda I is the ith eigenvalue, corresponding to ith eigenvalue, corresponding solution is known as the ith eigenvector. Solution is ith eigenvector. So, therefore, in the equation a x I is equal to lambda I x I. So, this will be the solution of the problem. Corresponding to lambda I will be having, corresponding to eigenvalue we will be having the corresponding ith eigenvector. Now, if we look into the characteristic equation p lambda is equal to 0, if we are talking about a 5 component system, then you will be getting a 5 into 5 square matrix, and degree of this polynomial will be order will be 5. So, therefore, you are going to expect 5 number of roots from this polynomial or 5 eigenvalues. Now, if it is a 10 into 10 matrix, if A is a 10 into 10 matrix, we are going to get a characteristic equation of degree 10. In that case, there will be 10 number of eigenvalues present in that case. So, if it is a simple system, if it is a 2 into 2 system or 3 into 3 system, the eigenvalues are quite, they can be evaluated analytically. For 2 into 2 or 3 into 3 matrix, eigenvalues are evaluated analytically. For higher order system, we have to take recourse to some numerical techniques. For higher order systems, numerical solution is required. One can take recourse to Newton-Raphson algorithm to find out the first root, then one has to use the some kind of numerical method to evaluate all the eigenvalues or all the roots of this equation. maybe Horner's method may be one of them. So, by using such numerical technique, one can evaluate all the root of the characteristic equation P of lambda equal to 0. For the corresponding lambda, one has to evaluate the eigenvector, maybe Given's method is there to evaluate the corresponding eigenvectors. Okay. So, what are the physical significance of eigenvalues and eigenvectors? Eigenvalues are the eigenvectors are basically the characteristic coordinate system For example, for a 3-dimensional system, like any vector can be represented as the along the x axis, along the y axis, along the z axis. So, by the 3 unit vectors it can be expressed. Similarly, for an n-dimensional space, the eigenvectors will represent the mutually orthogonal directions. So, any vector can be broken down, can be resolved into these eigenvector directions, and in every eigenvector direction the corresponding value, the amplitude will be corresponding to the eigenvalues. That is the contribution coming of the original vector, the contribution of that vector into the direction of the eigenvectors will be represented by the eigenvalues. So, therefore, that is the physical significance of eigenvectors and eigenvalues. Now, there is something called algebraic simplicity. If all eigenvalues are distinct, they are not repetitive. If all of them are distinct, that means lambda I, they do not occur twice repeatedly. If all the eigenvalues are distinct, then this is the system is called algebraically simple system. So, what is the algebraically simple system? A characteristic equation where all the eigenvalues are distinct. Okay. Then next we will be proving some of the axioms or theorems which we will be using quite often in our course. So, the first theorem that we are going to state and prove is that theorem 1, left eigenvector of a matrix A is same as right eigenvector of corresponding matrix transpose matrix A transpose or vice versa. Now, to prove this thing, let us consider a vector in n-dimensional real space. Consider vector y belongs to n-dimensional real space. So, of course, the transpose vector also belongs to n-dimensional real space. Okay. Once we define this vector y and y transpose, then we consider the eigenvalue problem. Y transpose A is equal to eta y transpose. Suppose this is equation number 1. In this particular equation, y transpose is left eigenvector of matrix X, and eta is corresponding eigenvalue. The size of y transpose is 1 cross n, the size of A will be n cross n. So, since the number of rows, number of columns of A matching with the number of rows of y transpose, therefore, they are conformable and the matrix multiplication is allowed. Now, let us take the transpose of equation 1. If we take the transpose of equation 1, this becomes y t A transpose of that eta y transpose of that. You remember we have already taught in the earlier class that A B transpose is nothing but B transpose A transpose. So, therefore, this becomes A transpose of y transpose, eta being a scalar. So, it does not matter. So, it becomes y transpose and transpose of that. Now, transpose of a transpose matrix is nothing but vector is basically the same one. So, basically A transpose y is equal to eta y. So, again if you look into this equation, this is again an eigenvalue problem. The form of the equation is again an eigenvalue problem. Here the corresponding vector is A, corresponding matrix is A transpose and the eigenvector is y. So, y is eigenvector it is basically eigenvector of A transpose, and y is right eigenvector of A transpose because y is occurring in the right direction. So, it will be right eigenvector of A transpose. So, therefore, that completes the proof. Okay. So, we have proved that left eigenvector of a matrix is nothing but the right eigenvector of transpose matrix. Y is right eigenvector of the transpose matrix. So, we have proved our theorem, first theorem, then we go to the next theorem. This theorem says that eigenvalues of a real matrix is identical to those of transpose matrix. Eigenvalues of a real matrix A are same, identical, equal to those of A transpose. So, you have to prove that eigenvalues of A and eigenvalues of A transpose both are identical. So, we assume the associated eigenvalue problem. Consider following eigenvalue problem. We will consider a pair of such problems. First one is A x is equal to lambda x, and second one is A transpose y is equal to eta y. So, in this case x is the lambda is the eigenvalues of A and corresponding eigenvectors are x. In the second case, in the second problem, eta are the eigenvalues of A transpose and the y are the corresponding eigenvectors. Now, we have already seen that for a matrix, from the property of the determinant, that determinant of a matrix is equal to the determinant of the transpose matrix. So, therefore, we utilize the property for a matrix B. Determinant does not change whether the matrix is transpose or normal. So, determinant of B is identical to determinant of B transpose. So, therefore, we write determinant of A minus lambda I should be equal to determinant of A minus lambda I transpose. So, we just consider a matrix A minus lambda I as B. So, determinant of the matrix A minus lambda I is identical to determinant of matrix A minus lambda I transpose. So, we just open up this transpose operator here. So, this becomes determinant of A transpose minus lambda being a scalar multiplied by I transpose, but I transpose, since I is an identity matrix, it remains same. So, determinant of A transpose minus lambda I. So, therefore, we can from this equation we can write down that determinant of A minus lambda I should be is equal to determinant of A transpose minus lambda I. Now, since determinant of A minus lambda I is equal to 0, we can say that determinant of A minus A transpose minus lambda I should also be equal to 0. From this equation, determinant of A lambda equal to 0. So, therefore, determinant of A transpose minus lambda I should also be equal to 0. Now, look into equation number 2 and equation number 3. From the equation number 3, what we have got? Okay. So, whenever we have written that A x is equal to lambda x, that simply means determinant of A minus lambda I is always 0, and whenever we write A transpose minus eta I is equal to 0 or A transpose y is equal to eta y, this simply means determinant of A transpose minus eta I is equal to 0. So, from this we can compare this equation and this equation. So, if you compare this equation and this equation, what we will get? That determinant of A transpose minus lambda I is equal to determinant of A transpose minus eta I. That simply tells us that lambda is equal to eta. So, if you remember what is lambda, lambdas are the eigenvalues of the matrix A, eta are the eigenvalues of matrix A transpose. Since they are identical, so we can say that eigenvalues of A matrix A are identical with the eigenvalues of matrix A transpose. So, that completes the proof of the second theorem. So, we move over to the next theorem, and all these theorems are quite useful and helpful for solving the chemical engineering problems that we will see later on. So, next theorem goes like this. This says if eigenvalues are simple, simple means there is no repetition of the eigenvalues, they are distinct. If eigenvalues are simple, then eigenvectors form an independent set of vectors or a basis set. Okay. So, that simply that means that if for the simple eigenvalues, for distinct eigenvalues, the eigenvectors form an independent set of vectors or the basis set vectors. That means that was I was telling in the beginning of this class, that is the physical significance of the eigenvectors and eigenvalues. The eigenvectors represent mutually orthogonal and independent directions. So, any vector in the space can be represented as a linear combination of the eigenvectors. So, that is the physical significance of eigenvectors, and contributions in each direction of the eigenvectors will be dictated by the corresponding values of corresponding eigenvalues. Okay. Let us prove this, that eigenvectors they are mutually independent to each other. So, that they will be forming the independent as if they are represented by the independent axis, or these axes will be basically their independent directions. So, the proof goes like this. We assume there are r number of eigenvectors of a matrix, and out of these r eigenvectors there are n number of eigenvectors. In a system there are n number of eigenvectors, and out of these n number of eigenvectors, out of n eigenvectors, r number of eigenvectors are independent. That means, rest eigenvectors from the from n minus r numbers, they are algebraic, they are dependent vectors. So, we write x 1, x 2 up to x r, these r eigenvectors are independent. Now, in this notation, x j corresponds to lambda j. That means, for the eigenvalue lambda j, the corresponding eigenvector is x j. So, therefore, for any j lying in between n minus r to n, what is that? R eigenvectors are independent and n minus r eigenvectors are dependent. That means, any eigenvector. So, we have said that the total number of eigenvectors are n. Out of this n, r number of vectors are independent. So, what is n? This set lying in between n minus r and n is this set. That means, it is a dependent set of eigenvectors. So, therefore, any eigenvectors present in this set, it can be expressed as a linear combination of all the independent eigenvectors x 1, x 2, x 3 up to x r. So, that we have already proved earlier, that if there are n number of independent vectors present in a space, any other vector can be represented as a linear combination of these n independent vectors. So, therefore, x j can be written as a linear combination of all the other independent eigenvectors, and this index I runs from 1 to r, because r number of independent eigenvectors present in your system. This is equation number 1, but corresponding C I must not be equal to 0. So, this equation, why we write this equation? This equation represents a linear combination of vectors. C I x I are nothing but the linear combination of vectors. So, this is a dependent vector, and x i's, these are all independent vectors. Okay. So, let us go to the next step. So, we just open up this equation C I x I is equal to 1 to r. This is let us say equation number 1. We operate this equation by the matrix A. We have already seen earlier that matrix is like a function, it is an operator. So, we operate equation 1 by matrix A, like it is like differentiation is an operator, we are taking differentiation on both sides. So, it is like we are operating equation 1 by A. So, if that is the case, it will be A x j is equal to summation of A C I x I, where I is equal to 1 to r. Now, we open up this summation series. So, this becomes A x j is equal to A C 1 x 1 plus A C 2 x 2 plus A C 3 x 3 up to A C r x r. Now, each of them, so since C 1 is a scalar multiplier, this will be A x j is equal to C 1 A x 1 plus C 2 A x 2 plus C 3 A x 3 up to C r A x r, and we know that A x I is nothing but lambda I x I, that is the standard eigenvalue problem. For the corresponding value of lambda I, the eigenvalue, the corresponding eigenvector is x I. So, therefore, we can write A x j is equal to C 1, A x 1 is nothing but lambda 1 x 1. So, we write lambda 1 x 1 plus C 2, A x 2 we write lambda 2 x 2 plus C 3, A x 3 is lambda 3 x 3. Likewise, C r A x r is nothing but lambda x r. Now, so that is one equation we get. Now, we multiply equation 1 by lambda j, and okay. So, we can also write A x j as lambda j x j. So, we get this equation lambda j x j is equal to C 1 lambda 1 x 1 plus C 2 lambda 2 x 2 plus C 3 lambda 3 x 3 up to C r lambda x r. Next, what we do? We multiply equation number 1 with lambda j and see what we get. So, if we multiply equation number 1 by lambda j, we will be getting lambda j times x j is equal to C 1 lambda j x 1 plus C 2 lambda j x 2 plus C 3 lambda j x 3 up to C r lambda j x r. This we will be getting by multiplying equation 1 by lambda j. Then we subtract this equation from that equation. So, we do a subtraction here and see what we get. So, if we really do the subtraction, the left hand side will be equal to 0, and let us see what we get in the right hand side. This will be C 1 lambda 1 minus lambda j x 1 plus C 2 lambda 2 minus lambda j x 2 plus C 3 lambda 3 minus lambda j x 3 up to C r lambda r minus lambda j x r. So, let us say this is equation number 1. So, we get equation number 1, equation number A. Let us write down the equation number A once again for convenience. Lambda 1 minus lambda j x 1 plus C 2 lambda 2 minus lambda j x 2, likewise up to C r lambda r minus lambda j x r is equal to 0. Now, in this equation we have already, this problem is for algebraically simple problem. So, therefore, lambda I is not equal to lambda j. So, therefore, lambda 1 is not equal to lambda j, lambda 2 is not equal to lambda j. So, lambda 1 minus lambda j is not equal to 0. So, lambda 1 minus lambda j is not equal to 0. Similarly, lambda 2 minus lambda j is not equal to 0, lambda r minus lambda I is not equal to 0. So, therefore, in order to satisfy this equation A, to satisfy equation A, we must have that all the corresponding coefficients must vanish each and individual. That means, to satisfy equation A, compulsorily we should have C 1 equal to 0, C 2 equal to 0, C 3 equal to 0 up to C r, all of them should be individually equal to 0. So, therefore, this simply proves that whatever we have done in the earlier classes, that x 1 for this C I, each of these C I will be equal to 0, then x I x 1 to x r x 1 to x r, they form a set of equations, set of vectors, and we assumed these are independent eigenvectors So, therefore, x j, any other vector can be represented as summation C I x I, where C I is not equal to 0. So, that was our earlier assumption when we started, that we have taken up any eigenvector from the dependent set lying between j the n and n minus r, j being lying between n minus r and n. So, x j can be expressed as a linear combination of these vectors. So, therefore, we assume that C y was not equal to 0, but in this case whatever we have proved, that it goes to the contrary of our assumption that each of them will be individually equal to 0. So, we have proved that C I must be equal to 0. So, it contradicts of our assumption. So, it is contrary to our assumption. So, this is called a negative proof. So, what is the implication? The interpretation is that the rest eigenvectors, the x j eigenvectors, which a set lying between n minus r to n, they are not dependent set of vectors, they are also independent set of vectors. X j are also independent set of vectors. So, therefore, all the eigenvectors are independent set of vectors. Therefore, all eigenvectors are independent. All eigenvectors are independent and they constitute the members, they are the members of the basis set. So, they form a basis set. This completes this proof. So, we have seen that all the eigenvectors of a matrix A are basically their members of the basis set, and basis set vectors, any other vector in the space can be represented as a basis set vectors. So, therefore, eigenvectors of a matrix are always independent, each of them is independent, they are the members of basis set vector. So, any other vector in the space can be represented as a linear combination of all these eigenvectors. So, therefore, as we have we said a few minutes back regarding the physical interpretation of the eigenvectors, that eigenvectors are nothing but the directions which are mutually independent to each other, and any other vector in the space can be represented as a linear combinations of these independent vectors. Okay. So, next we go to the fourth theorem, theorem number 4. This says eigenvectors of x I, eigenvectors x I and x j correspond to, if eigenvectors x I and x j correspond to two distinct eigenvalues lambda I and lambda j, then if eigenvectors x I and x j correspond to distinct eigenvalues lambda I and lambda j, they are orthogonal to each other for a real symmetric matrix. For a real, if this is the case, then for a real symmetric matrix, x I and x j are orthogonal. Okay. And symmetric matrix means A is equal to A transpose. Therefore, if we have, so what is the proposition in this theorem? In this theorem, it is proposed that if we have a real symmetric matrix, that means A is equal to A transpose, then two eigenvectors x j and x I, they correspond to, if they correspond to two distinct eigenvalues lambda I and lambda j, then x I and x j form an orthogonal set. That means, they are orthogonal to each other. So, therefore, we prove this theorem, and the proof goes like this. Let us say lambda I and lambda j are two distinct eigenvalues, corresponding eigenvectors are x I and x j, and let us write down the associated eigenvalue problems with the linked with the eigenvalues lambda I and lambda j. So, we write down the associated eigenvalue problems. A x I is equal to lambda I x I, this is equation number 1. A x j is equal to lambda j x j. This is equation number 2. These are the associated eigenvalue problems for lambda I and lambda j. Then what we do? We take the inner product of equation 1 with respect to x j. Take inner product of equation 1 with respect to x j. If we take the inner product, we will getting x j comma a x I is equal to inner product of x j lambda I x I. So, if we remember that we have proved this equation in the last class, x inner product of x j and x I should be x j A transpose. So, therefore, so this will be inner product of x j and we write it in the other form. We will be doing that later on. First, we take the inner product of equation 1 with respect to x j and we will be getting equation number 3. Then we take inner product of equation 2 with respect to x I on the right. So, let us see what we get. Now, from these two we will be getting inner product of x j A x I is equal to inner product of x j lambda I x I. Second, the inner product of the second equation with respect to x I. So, A x j comma x I is equal to inner product of I x j is nothing but lambda j x j, the inner product of lambda j x j and x I. Now, we subtract these two equations. If we subtract these two equations, what we get is that inner product of x j and A x I minus inner product of A x j comma x I is equal to we can take we invoke the property of the inner product that x lambda inner product between x lambda y is nothing but lambda inner product of x and y, that is the if lambda is a scalar. So, similarly, we can do here we can take lambda I out. So, this becomes x inner product between x j and x I minus same here we took lambda j out. So, it will be lambda j multiplied by inner product of x j and x I, and we have already proved earlier that inner product of x j x I is identical to inner product of x I x j. That means, these two are identical and we can write lambda I minus lambda j multiplied and inner product x I and x j can be taken as common. Then we utilize the formula that whatever we have derived earlier, that inner product between x and y should be is equal to x transpose y, that we have already proved probably in the last lecture. So, utilizing that we will be doing x j transpose A x I minus A x j transpose full x I is equal to lambda I minus lambda j inner product of x I and x j. So, just open up this transpose. So, what we get x j transpose A x I is nothing but x j transpose A transpose x I. We utilize the formula A B transpose is nothing but B transpose A transpose. So, x j transpose will be coming in the front. So, it will be x j transpose A transpose x I is equal to lambda I minus lambda j inner product of x j and x I and x j. Now, if you see the quantity on the left hand side is that the left hand side will be having the identical quantities, one with the negative sign. So, these two will vanish. Now, we have already seen. So, what we get from here is that 0 is equal to lambda I minus lambda j inner product of x I and x j. Now, lambda I, the eigenvalues being simple in nature, that means they are distinct. Distinct means lambda I is not is equal to lambda j, they are not repeated roots, they are distinct roots. So, therefore, to satisfy this equation, inner product of x I and x j should be equal to 0. So, therefore, since lambda is not equal to lambda j, this quantity is not equal to 0. Therefore, to satisfy this equation, only option left is that inner product of x I and x j must be equal to 0. So, therefore, that simply means that the eigenvectors x I and x j are orthogonal. Okay. So, just one more clarification is that in this equation, whenever we are omitting the left hand side, we are putting left hand side is equal to 0. If you look into this equation, x j transpose A x I minus x j transpose A transpose x I, but since it is a symmetric matrix, A is equal to A transpose. Therefore, since A is a symmetric matrix, these two quantities become identical and they will be subtracted. So, therefore, this whole left hand side will become 0 and you will be getting this equation. Since lambda I and lambda j are not equal, they are distinct, they will be not equal to 0. So, in order to satisfy this equation, x I inner product between x I and x j must be equal to 0. So, they are orthogonal to each other. So, therefore, if we have three dimensional system, for 3 dimensional system, we have 3 distinct eigenvalues lambda 1, lambda 2 and lambda 3 corresponding to 3 distinct eigenvalues. You will be having 3 distinct eigenvectors x 1, x 2, x 3. Now, this simply means that for the symmetric matrix, for symmetric, of course, square matrix, because eigenvalue problems are defined on square matrix only. For symmetric square matrix, x 1 inner product of x 1 and x 2 is equal to 0, is equal to inner product of x 1 and x 3 and equal to inner product of x 2 and x 3. This simply says that the eigenvectors are orthogonal to each other if we have a symmetric matrix. The other is not true, that if the matrix is not symmetric, that we cannot say the eigenvectors are orthogonal to each other. That may not be the case if the matrix is not symmetric, but in that case the eigenvectors of a matrix A and the eigenvectors of matrix A transpose, they form an orthogonal set. So, that we will prove in the next class, and after that proof we will be able to take up any chemical engineering problem and solve them by this eigenvalue eigenvector method. Okay. We stop in this class at here and we will take up from this point onwards in the next class. Thank you very much.